from here, stadium, and today I talk about I think recently I talk about short course and electricity, and I'll explain what this picture is again of this. And these are my collaborators, it's the Oparani from Weizmann and the student here. So let's start with what we now we know what happens if you break any object. Okay, we more or less know all objects are made of molecules, and if you break the molecule with identical collisions, you get atoms, and the atoms are also non-fundamental particles. These are made up of nucleus and electrons. Electrons revolve around the nucleus, and inside the nucleus also you will see that number of protons and neutrons. And you all are familiar with this structure up to this point maybe, or also you might know that protons and neutrons are also non-fundamental particles. They are made of quarks. So till now we know that this is the end point and quarks are not divisible till now, but then we can have more and more dynamic experiments which doesn't seem very probable. It might be true that quarks can be divisible into other particles, but we now don't know. So we will stop here and we will talk about these particular particles and we will try to understand how to explain various interactions between this. Okay, and these are the length scales for each object. Like what kind of length scale you are going to go. Okay. Now these elementary particles can feel various kinds of forces. Okay. And we are more or less familiar with the way. These are gravitational interactions, and we are still familiar with gravitational interactions. Learn about it in the past in our export. Electromagnetic is also popularly known, but we don't study it so far like in the beginning. But this is also in daily life we experience electromagnetic force. We see lights, and we are all due to the electromagnetic interactions between various molecules and the less known forces are strong force and weak. Okay, so today's talk will be about the strong force and why we need it, how to explain this, and what kind of theory leads to this, and how to deal with this particular interaction. So, before going to strong and weak force, let's compare gravitational force and electromagnetic force. So, when I say strong, for the strong force, I want to strong. So what about the value? Who is stronger? Okay. So if you take an example for a proton and you take two protons, okay, and you check the gravitational force between them and the electrostatic force between them. Okay. So the gravitational force is just gm square by r square, electromagnetic force is e square by r square, and if you use your well-known CGS numbers, and you will get the number to be 10 to the minus 36. So what you are seeing in this number is gravitational force divided by electromagnetic force is 10 to the minus 33. That's an extremely low number. Okay. So that means that gravitational force between two protons is extremely low with respect to the electrostatic force or electromagnetic force field the two protons will feel. So that means any dynamics between two charged particles will be majorly dominated by electromagnetic force and no gravitational force can act. So in that sense, the electromagnetic force is extremely stronger than the gravitational. Okay, and this is usually true for any charged particles. Okay, that build the electromagnetic force is much stronger. So to get any effect for gravitational force, you need neutral particle. If there is no charge, there is no electromagnetic force. It will be total zero, and then you will feel the gravitational. So whenever you see situation where gravitational force is very important, then you will see you are dealing with neutral particles. Yes. Now, we understood what is the comparison between the electromagnetic force and gravitational force. Let's look at the nucleus and the atomic structure. And take an example of carbon 12. This is complete very good picture of this from the internet. And if you the first picture you will get in the internet for carbon. And you can ask whether this atom is stable. Okay. And you can say that yes, there are electromagnetic force between this core nucleus and the charges. There is attraction and there are electrons are revolving. So there is a equilibrium between them. Okay, and these are well understood within if you just put kinematics and electromagnetic. So you don't need anything else. It is extremely stable. Now you can ask, is the nucleus itself stable? This core. This is an extremely small object. The radius of this object is very small. And in that small region, you have six, or you have six protons. And all of the protons are positively charged. And they are sitting almost close to each other. So you can ask whether, so there will be electromagnetic repulsion between two protons, right? So the electromagnetic repulsion between two protons will be so high, it will become the whole object. But carbon is it's extremely stable now. I mean, the nucleus is also extremely stable, you cannot break it. So you can ask, so what is helping them binding together in such a small region? And all of you are part of the rubber coupling, and you know how small the nucleus size is. And in that small region, you have so many protons. Okay, and so that's when the question comes that whether this nucleus is stable. So electromagnetic repulsion between the positive charges should be extremely high and it should recover everything. But it is stable, so that means we need another strong force. Okay, electromagnetic force enough is not enough to explain the stability of the nucleus. So you need a stronger force for this, and that's what we will be talking about. Okay, so before going there, we should recollect how we learned about force. What does it mean by force? And the definition or understanding of force has changed throughout history. In 1700, more or less near 1700, Newton gave the equation of the law of motion, and all of you have learned this. And this is more or less the first definition of force. Okay, this is when he explained what force is. Okay, that's the first definition. And mass times acceleration force, and you can measure it by putting a probe particle, you check what is actually getting the force, and you know what is the force. Next, drastic change in understanding of force is as you have an electrostatics. Yeah. Now in electrostatics, what we explained that force is nothing but there are some electric lines of force. And this is at a particular region, you check what is the density of lines, like how many lines are crossing through that volume. So that's simply giving you the definition of force. Okay, so that's a significantly different understanding than this one, and it is a radical one. But both of them, if you observe when you will see what Feynman said about force. So what around this time in 1940, mid 1900, 19th century, what it said that force is thought of as exchange of particles. So if there are two electrons and protons are going, okay, so the force cannot be, so it should be thought of as a exchange of various particles. For this electromagnetic case, this is electron plus, electron minus, there will be an exchange of proton. Okay, I will explain in more details why this is true, but this is drastically different from the interaction between the same electron and proton picture Faraday. So here okay, so in more detail, so let's know more about what we have said. And so if you look at Newton's and Faraday's picture for force, you will see that the nature of force is instantaneous. Okay. Now, what do I mean by instantaneous is whenever you have a charge or positive charge and you put a negative charge, the negative charge will feel the force of the positive charge instantaneously. So that's what Newton said, that's what Faraday said. Okay. Now, at that time, the 1700 or whenever they were studying those objects, the particles were not moving very fast. I mean, the experiments they were interested were very slowly moving, or maybe in those cases, almost a static particle. Okay. And extremely non-relativistic, to be precise. Like they are not going at the speed of light. So that's why, so in the previous picture I said, the force would be thought of as an interaction through a photon particle. Now photon usually travels in a speed of light. So if any particle traveling much lower speed than the photon, then you shouldn't be worried whether the force is instantaneous or happening in the speed of light. I mean, both of them are almost equivalent. You won't care. So that's why Newton or Faraday didn't need to think about what time it takes to interact with each other. But we intuitively know that the force should not be instantaneous. I mean, it should take some time. Otherwise, there will be non-local interactions, and this will it will complicate the whole world a lot. So we don't want that complication. We want to simplify. So this idea. Okay. So that particular idea came up from Maxwell's equation. In 60s, after 30 years after Faraday, Maxwell proposed these equations, and what it determines is the electric or magnetic field due to charges or the motion of charges. And motion of charges means current. Okay. And important development in this particular, this was more or less known. What is electric force and what is magnetic force? Everything was known. The major change in the understanding is the same equation for zero source. If you put the charge density and the current to zero in Maxwell's equation, yet you will get a constant solution to the equation. And the solution is electromagnetic wave. And that means it's a photon. Okay. So this is like in the quantized version it's called photon, but it is effectively electromagnetic wave. So that's a solution to the same equation, which dictates the electromagnetic fields. Okay. Now think that whenever you are solving for Gauss law, for example, okay, for a point charge particle, okay, the space where you are solving the equation, that's totally empty. Charge is localized at a single point, let's say the origin of the space. That's where the charge is. So the equation is local. You are solving the equation almost for the full space as an empty solution. There is no charge at all. Okay. But there are boundary conditions which is like a point charge. Okay. So the point I'm trying to make is whenever you are solving Gauss law for a single point particle, point charge particle, okay, the equation you are solving is almost for an uncharged solution. There is no source in the right hand side because the source is only at a data function localized at origin. So whenever you are at the origin, like you are solving the equation at the origin, you have to put the charge in the right hand side. Otherwise, you have to put zero. So you have two situations. One is electromagnetic wave. Another one is an electrostatic force around a charge. And both of them are zero charge equation. And that means that in the so whenever you think of an electrostatic force around the charge, you can think that it is almost filled with a lot of photons because that's the same equation you are solving. So how can you add that the electric field or magnetic field is coming from a electric charge or a photon? So you don't know, you can't distinguish. So that's why Feynman said that charges talk to each other using exchange of photons. Okay. So but these photons cannot travel too far. These are virtual particles. So I'm not explaining that part, but this is a very important point that when you are solving for electrostatic force, like Gauss law, just a simple del dot E is equal to rho. Okay, you are basically solving for the density of photons you are getting at a particular free space. Okay. Now note that interaction through the exchange of photons is not instantaneous. It will happen at the speed of light. Okay, it will not be instantaneous. So if you have a situation where particles will move in a speed of light, then you will see the effect that the forces are not instantaneous. But otherwise, you will not feel it if all other particles are moving in a sub light velocity. If it is moving in a very much less like non-relativistic velocity. Yeah. So
that more or less gives you an idea how to think about the charges which are talking to each other to exchange the photon. Okay. Now let's change the topic to something else, and that's our Feynman diagram. Okay. And consider a particular integral. Say a very simple integral. You must have done such an integral in your class. You look at this integral. X square e to the minus x square. Take lambda is equal to 0. Just assume that lambda is equal to 0, right? Okay. And you try to do this integral. I don't know, but many of you have seen this integral, and you can do this integral. Okay. If lambda is equal to 0, you can do this integral. These are called Gaussian integrals. Okay. And many of you have seen this. So this is doable. But if you deform that integral by lambda x to the power 4, just add another term, lambda x to the power 4. Okay. Now I want to calculate this x square average for this lambda x to the power 4. And it is called anormally Gaussian distribution. It is anormally because it is deformed by lambda x to the 4. Okay. For this integral, there is no exact solution for lambda. For a particular values of lambda, you don't know how to do the integral. Okay. I mean, you don't know means you can know, but I don't know yet. And no one else have done this analytically yet. Okay. By the way, you can ask any question you want in the middle also. And there is you should understand this and you can ask. Okay. So as I said that if lambda is 0 for this integral, if lambda is 0 for this integral is doable, and the answer is square root pi by 2. You can easily check. But if you take lambda to be 10 to the minus 2, and the answer is 0.558, that's not important. The important point is, of course, numerically this integral can be done. If you put it in a computer and it will do it instantly. Okay. Now you can ask how to do it analytically. Is there a new way you can do this integral analytically? Okay. So to do the analytical integral, what you can do is you can do a small lambda expansion. Okay, what is happening here? You look at this particular function, you go minus x square minus lambda x to the 4, and lambda is small. So what will you do is you take out this e to the minus lambda x to the 4, and you do the exponential expansion. If you have seen this exponential expansion, e to the power x is 1 plus x by x plus x square by 2. That's the same formula I use. So this is the expansion. Since lambda is small, I can do this expansion. Now you see that each integral, so individually can be done. X square e to the minus x square can be done. X to the 6 e to the minus x square can be done. And you must have heard the trick that you have to put a parameter inside and then you take derivatives to generate all that. So the point is that these integrals can be done individually. Okay. So this is like an infinite series with each integral doable integrals. So the final answer is, you can easily check that this is the answer. That the limit term, as you said, if you as you saw that lambda is equal to 0, square root pi by 2, and then these are the corrections to the integral. Now you can ask why I am showing this particular example of some integral, that will be clear in this next line. That so you saw this doing this integral was hard analytically, but it became simple when you did the expansion. Now if you can find a way to write down any quantitative, so if I ask you what is the lambda to the power 100 contribution of this integral? Okay, let's say I am asking you that question. What is the lambda to the power 100 contribution of this integral? How will you do it? So you need some principle. You can't. So this is an exponential division. It might be easier, but you need some rules. So we'll set up the rule. Okay. So the rule is this. Since you have an x square integral, you are doing an x square average, you will put two open legs. Okay? Since you have an x to the power 4 interaction, you will have vertices which will, from where 4 legs will come out. So in each diagram, 2 legs will be open and other 2 have to be joined. So if you look at this point and this point, each point, 4 lines are coming out from that point. If you can see, those are representing the x to the power 4. Okay, this x square average is represented by 2 open legs. Okay, and this x to the power 6, why it is coming? You have 2 x's in the ends, and you have 4 x's coming from this vertex. X over 4 coming from this vertex. And you have to put a lambda. So that's the rule. Okay. And you can ask how are you get these two factors, if there is any. This comes from the symmetry of this diagram. You put a line and there is a symmetry that you exchange these two, there is no change in the answer. So you have to put a 1 by 2 factorial factor. So I am setting up that rule for this integral. But you can ask that just to do this integral, why are you complicating the whole thing to represent it like a diagram? But this is very important. This will become very important in next step. Okay. Now this will become very complicated when you will consider the same x square average for a different distribution, and it's a 2 variable distribution now. You have 2 variables x and y. Okay. And now again, it's minus x square minus y square. It's a good distribution. Okay, it's a good probability distribution. You have a deformation lambda x y square. Now you have to do this integral. Now here it becomes very complicated. Now you can ask again, you want to calculate x square average. How will you calculate? What you will do is using the same rule, as I said, that x represents a black line, y represents a red line, and x y square will represent a black line connected to 2 red lines because there are 2 y's. You see? Now that you play the same game, you try to construct 2 open black legs because I am calculating x square average. There are 2 x's, so there are 2 open legs. Now you start filling up various diagrams. What you will do that each vertex you can see here that here you will always have this kind of vertex. You will not have anything else other than the vertex. So the rule is this, that you draw any diagram you want, but you have to follow this rule that this vertex will come where only 1 black, 2 red legs should be there. So you see 1 black line and 2 red lines are coming out of this vertex. Here also the same. Okay. Given this, you can write down that expansion. I showed in the previous. This expansion can be written down explicitly for any lambda power. Okay. Now these two will come very soon. Okay. In the QCD. And this will be very important. So the point is this, that you were trying to do some integral which was complicated. Here it is not looking like complicated, but it will become very complicated soon. But you want to do the integral, and these were very complicated, let's say. Now you want to know a particular lambda contribution. It is good to have a picture or a diagram corresponding to each whatever contribution you want to calculate. So you are trying to replace a complicated mathematical expression by diagrams. That's all Feynman did. And that is the only reason. And that is the only reason that Feynman got the Nobel Prize. I mean, that's very important. Because you want to calculate a perturbation like this and integrals. And if you can write down, if you can to replace the whole mathematics by some diagrams, that simplifies your life. That makes your life easier. So that's very important development. Now this you can use later. Okay. So again, coming back to physics. Okay. All of you must have heard or did the experiment in the lab, double slit experiment. Okay. Okay. So what you do, you have a light source, and you have a block like where the light is getting blocked, and there are 2 holes in that block. There are usually slits. There are 2 slits, and this is a screen where you put throw that light, and you get some pattern here. Right? Okay. Now, if you have done the optics theory, you must have seen that what to do to get this particular pattern here. You get the pattern by summing over the phases you acquire through these 2 paths. Okay, and you add them up, and you get the pattern. Okay. So this is so these are photons can go through any of these slits, and the idea is that it is probabilistic. You don't know which path it will take, so you sum them up. And in quantum mechanics, what people do is they only calculate probability. Probability between, let's say, probability of particle going from this source to the end screen. Okay, so you are trying to calculate some probability. The probabilities are calculated usually through summing over various phases, and it is also true in optics. Okay, so that's what you do. So that's what Feynman started with. Okay, Now what he did, he added another hole into the picture. Okay. Now you have the same slit, but you have added another slit. So this is a three slit problem. What you will do, you will add another phase here due to the third path. Okay, and then add, and the pattern will be complicated, but this will give you the answer. Okay. Now, if and what you are calculating is the same thing, that the probability of the photon to go from this source to the screen. That's all you are calculating. The photon will travel from the source to the screen. What is the probability? You are going through three paths, and you have to sum over three phases. Now you add another blocker with two slits, like double slit, another double slit. In front of that, now what you will do? You have to keep track of all the paths the photon can take. Like the particle can go from here, and it can choose to go here, and it can go here. Okay. So there are total 6 possibilities if you can count. Okay. And you have to sum up all the paths. Yeah. So if you have a double slit with the three, say, and there are two blockers with 3 and 2, you have to go through 6 possibilities, and you have to add all of these phases to get the pattern. In fact, in your experiment, if you actually do this, you will match the experiment with this particular idea that you have to sum over all the paths. Okay. Now you keep adding such blockers with holes, with slits. Okay. And you increase those number of blockers to infinite. Now you think that there are infinite number of blockers, like double slit. I am calling it double slit, but it is multi-slit now. And the number of slits are also going to infinity. That your slit number is also going to infinity. So it is almost full of holes. Like the holes is filling up the whole screen. Like and what you have to do, you have to take all possible paths to go from one point, this light source, to the screen. And what you have to do, you have to sum over all the paths to get the screen probability, right? So again, you are calculating the same thing. What is the probability for a photon to go from the source to the screen? And now you have a very complicated experiment, but it is a theoretical thought experiment you are doing. And what you will conclude in the end, that if there are infinite number of slits, that is equivalent to there is no slit at all. Think of it. This is a screen with an infinite number of slits. It's filling up the whole thing. So there are too many holes. So where is the slit? There is no slit at all. Okay. And that means what you are doing is, even if, so that means previously it was there are probabilistic there are probabilities associated to each path. Those were discrete in numbers. Now it became a continuous problem that you have. So now what you will do is, you take a photon and it can go to anywhere, and it will go to this point finally, and you are calculating all possible paths. You are checking all possible paths, whatever it can take, and you associate a phase to that particular path, and you sum over all the paths. And that will give you probability for a photon to go from one point to another in an open space. So in open space also, in principle, photon can take any path. Okay, that's a very important idea in quantum mechanics. Couple of you might have heard that, but otherwise it's an equivalent idea to what you learn in quantum mechanics, quantization. So this is called path integral of find. So I'll come to that, but this is a very important idea that you are seeing that quantum mechanical process. So what you're saying, that the photon is not going in a straight line. It can take any path, and there are probabilities associated to each path. You give an weight, that's the phase for the path, and then you sum over them, and you get the final probability for a photon to go from one point to another. Okay, that's very important. If you have any question, you can ask. Okay, so if this is more or less, if all of you have understood, let's go to the next slide. So this is Feynman's quantum mechanics. Okay, this is a pure quantum mechanics that what you have to do to calculate any probability in quantum mechanics, that you sum over all possible paths going from one point to the another, and you add all of them, and whatever answer you will get, that is the probability for going from one point to the another. Okay. Now, Feynman proposed this definition for wave function, and it's a radically changed definition from Schrodinger. What Schrodinger said, it is an extremely different definition. Yet, both of them matches exactly. So that's the main point, that they are totally agreeing with each other. Yet the idea is extremely different from our study basis. Okay. Now now you can ask, for photon you know how to calculate phase. Okay. For any other particles, if it is just a single particle quantum mechanics, how will you set the phase? And Feynman took an assumption or educated guess. The educated guess is this phase will be the action of the particle. And action, what is action? It's an integral of the Lagrangian. All of you have heard of Lagrangian, I'm sure. That what is Lagrangian? It is kinetic term minus potential term. That's all it is. So for a particle, for point particle, what it will be half mv square minus v of x, if your potential is v. And that's all it is. Okay. So this is the action. So for a single particle, so what you are doing? You are calculating for probability for a particle to go from point 1 to point 2. What you will do? You will sum over all possible paths. Any arbitrary possible paths. You calculate this action for that path and you sum over all. So it's an infinite number of sum you see. And whatever answer you will get, that will be the probability for the particle to go from one point to another. Okay. And this is explained in Feynman and Gibbs. This is the picture of that very old book, but it is the form has changed now. Okay, so if we are all in the same page for Feynman's quantum mechanics, okay. Now let's understand what is quantum fields. How to think of fields. We can think of fields like this. That for particles, we all know what is the degree of freedom. The degree of freedom of the position of that particle. Okay, that's like x vector of function of field. Okay. And as I said, that to get a probability for that single particle, for example, this harmonic oscillator, to go from one point to another, how to calculate it? You sum over all possible paths the particle can take. Okay. And what you do, you sum over so this is a notation, this bracket with dx represents that you are actually summing over all possible paths. Okay, the particle can take. Okay, but you understood what the sum over all path means, like in the previous slide. Now that's a mathematical notation. It's nothing more than that. You just integration means summing over all, and this is the probability. Okay, this is the quantum mechanics for particle. Now you can ask what are the field, what for the fields. Now before going there, you have to understand what is field. Okay, what is classical before going to quantum field? Classical, how to think of that? Look at this picture. Okay, Feynman's is playing Mongo. Now I'll call it drum. And in the drum, you will see that there is a while you play drum. If I ask you what is the equation of motion for the drum surface, can you write and become the equation like x double dot is equal to f or whatever like that for the drum surface? You cannot write it because each point of the drum can move in a different way, and that will be an extremely complicated object. So you have to write something else. So that's basically, so if you can write down that equation of motion for the drum, and for example, let's say height. So let's say when it is in equilibrium, when no one is playing it, it is 0. Let's say height is 0. Now you start playing it, then the height will change. In various regions, the height will be very different, right? So you represent that, let's say height is represented by 5. And it is function of the x. Now what is this x? X is the 2D surface. Okay, that disk or whatever you have. That's the x. And that height will also be a function of time. It will not be fixed at some. So it will oscillate. So it will be a function of time. So this is like a field. It's a continuous variable. There can be infinite. You can think of it as a coordinated motion of infinite number of particles. Okay. So this is interesting, and this is like now another field example you know is electromagnetic field. Okay. That's like electric field, function of position and time. So at any position you can calculate what is the electric field, and that's one of time. Now that's electromagnetic field. Now here, if you want to do quantum mechanics, if I ask you start from a particular electromagnetic field and you go to the another electromagnetic field, this is like initial and the final coincidence of X. I asked you what is the quantum probability of going from that particular field to another field configuration. Okay. Now that's So if you have a classical theory, you must have a quantum theory also. That's like, I mean, you have to get it. So you are trying to get it. Okay. Now you will ask that previously what you did is you set an initial condition and final condition in terms of this X vector, that position of the particle and position of the final position of the particle and the initial position of the particle. Here what you are asking, final electric field configuration and initial electric field configuration. And now in between, you will scan all possible functions you can write down in terms of E. You see, previously it was all possible functions of X of T you can write down. Now it's like all possible function of electric field of the height function, whatever you can write down. So you have to sum over all such configurations. So that is represented by this. So this will calculate the probability of a drum going from a particular configuration to another. So you start playing it, it will start moving. So this usually you won't see it in usual life because all the particles are classical, all dynamics are classical. You won't see the quantum field situation. But in electrodynamics you will see it because electromagnetic wave, and if you quantize it, those are the photons are highly quantized objects. I mean that field needs quantization. Okay, drum doesn't need quantization, I mean, whatever I'm playing, but electromagnetic field needs quantization. Photons are extremely quantum. And that is called path integral. Okay, you sum over all possible paths, that's path integral. Okay, now for whatever, if it is electromagnetic field or drum you want to try to quantize, you have to sum over all possible configurations you are trying.
Sir,
Good.
I was asking that the action.
Yeah.
For quantum mechanical particle, how can it be the action would be same as the classical particle? Means there is no quantization or something like that is necessary.
No, it's a different way of thinking. What you are doing is let's say, it's an interesting question. And the one line answer is you are trying to go from one point to another point. And usually, let's say there is no force, the particle will take the straight line path classically. We agree with that? Classically, you take that path. But while doing the sum of all paths, okay,
And include those possibilities.
you will include all possibilities to go from one point to another. And these are, if there are contributions coming from those arbitrary paths, that means the particles are not actually taking the classical path. There is an uncertainty in the position. You can't determine which path it is taking. There are probabilities, finite probabilities to go in this path also. So this classical path will take the maximum probability. So that means in quantum problem, if you have a maximum probability path, that will be called classical path. That's what the particle will take eventually, I mean most of the time. But there might be a situation if the particle is subatomic. I mean if the particle mass is very small, there is an electron. Electron might take two paths. Okay, so if the mass is very small, if the particle is like very small, then it might take multiple other paths, nearby paths, and that means the particle has an answer. And that's how quantum mechanics idea is coming in this picture.
Understood.
Yeah. Okay. Okay, so we more or less understood what is classical fields and how to quantize it. You have to sum over all possible configurations, fields, and now what is quantum electrodynamics? Now again, the same thing. I mean, whatever I said, that now what are the fields in electrodynamics? You all know that you need photon fields. I wrote photon fields. It is electromagnetic fields, like just electromagnetic fields. You have electric field and a magnetic field. That's all it has. And you can have electrons because any charged particle, I mean electron means any charged particle, because it will interact with the electromagnetic field due to the charge. Now what you have to do is you have to sum over all possible configurations. The psi is representing the electron probability. If an electron moves through a space, there can be uncertainties. So you have to sum over all possibilities of the distribution, right? So what you will do, you will sum over all possibilities of the electromagnetic field, I mean electric field, magnetic field, and the psi field also. And there will be a complicated action for that. I mean the kind, whatever, the Lagrangian for that field. So you have a Lagrangian. So the Lagrangian for electromagnetic field, if anyone of you know, is V square minus V square. Okay. You can easily check that if you vary this equation like you do in classical mechanics, how to get an equation of motion for a Lagrangian. You vary the Lagrangian and you get an equation of motion. Right, there is equation of motion related to a Lagrangian. So you vary this equation and you will get Maxwell's equation. So this is where you can derive Maxwell's equation. And this is nothing but the energy density stored in a particular position. For electric density, square is the energy stored in a point. Now again, the similar kind of object, like the kinetic term for the fermions is like psi bar. Psi bar is conjugate of psi. It's not important, but it is just a complex conjugate. Let's say, okay, psi is almost same, and there is a derivative in between. So there is a derivative. There are two sides, okay, and there can be interactions. Interaction means, so fermion can interact with the electromagnetic field because that's what happens. That's why you can see lights, that there is an interaction between your eye, which has fermions, and the light. So there is an interaction. So we'll talk about this later. But you understood the point that this is the action. You put it here and you sum over all possible paths, and you will get the quantized state. Okay, and that's what Einstein did in 60s. And you sum over all possible functions for E, B, and psi.
So what is that inside that?
This is just a notation to say that we are summing over all possible configurations for the electric field or magnetic field or whatever function it can take. Okay, so you are basically summing over all possible functions, right? Previously, what you did, you summed over all possible positions of the particle for quantum mechanics. Now you are doing fields, so you have to sum over all possible functions for the fields. So this D is just a complicated version of dx. You write dx in integral dx, x square, x, whatever. That's a simple dx because there are only one variable you are integrating. Here you are actually integrating over infinite number of variables. Why? Because these x and p are there are infinite number of fields you are actually integrating. Okay. For example, for the drum, the height at a particular position is a single harmonic oscillator that can oscillate by itself. The second one, the next point can oscillate by itself, and in the total drum, how many points you are counting? There are actually infinite number of points. So when you are summing over all possible particles, they are independent motion. You are actually integrating over infinite number of directions. So yeah.
I was encountering that basic protocols and introduction to electronics. There is so that reactor or something like that was included with the introduction of fermions.
And Dirac proposed the fermions, the presence of various fermions, and I will put this interaction down later, and you will see that how actually fermion can interact with the photon. But what was the question?
Is that or something kind of encounter, and there is no that interaction were explained by that using this director.
I agree with you, and you will see what that interaction will look like. And whatever you are saying is will come in the next slide. Okay, so now what you are trying to do, you are trying to sum over all possible functions, E, B, and psi. You just saw that you have to sum over all possible functions. And then you have an action for this. This is the kinetic term for the electromagnetic field. This is the kinetic term for the size. And this is roughly like a potential. Okay. So that's the same action, like kinetic term minus potential. That's the same thing we are doing. So this is the Lagrangian for this complicated object. But anyway, that's not important. The important point is the unpaired singularity with the integral I explained previously. The dx dy and then 0 minus x square minus y square minus lambda x y square. Now, what is the similarity? The similarity is this: p square minus b square. The p you are integrating over. It's a quadratic function. Like square is there. P square and b square. This is like x square. This is like psi bar psi. This is like there are two sides are there. It's a psi square kind of an object. And this is like y square. And the interaction is like a psi bar psi. Now, I'll explain what is this. But you just identify lambda with e. Okay? Lambda is a constant there. Here, e is a constant. This is basically electron charge. Due to charge, there is an interaction, right? So if charge is 0, there is no interaction. So it should be proportional to E, right? Good. So E is there. Now A is like X. Why? X was identified the electromagnetic field. Now what is A? A is just the vector potential. You must have heard of this. The scalar potential and the vector potential. So how electric field and fields are calculated, connected? gradient of the phi is E and the curl of A is B. So these are linear relations. These are one-to-one correspondence there. So A interacts with the psi and psi. There are two psis. Okay, good. So this is like the same thing we saw here. So you will incorporate the same integral, and to be precise, if you don't have the interaction, you can do the integral exactly. Like you could have done the integral here if you don't have lambda. You put lambda to 0, you can do the integral. And here also you can do the same integral. This is exactly the same integral. It's just that there are infinite number of variables involved. Okay. Good. So due to the interaction, you can't do the integral, and they will do a similar perturbation in this lambda and this E. Okay. And you will get similar diagrams corresponding to this integral. Okay. And this is an extremely hard integral. Swinger did it without incorporating any diagrams or anything. Swinger was extremely talented, and he did the integrals without any help, and he just did this particular integral. Now that's an extremely hard. This is Swinger, but I can simplify it using his diagrams. So he wrote it in terms of pictures, particles coming in, particles going out, interacting through photons. All these diagrams, he drawn diagrams and he calculated all this thing much easier. That's very important. That he helped. Okay. So what it helps? You already had the answer. I mean, Swinger did it. So why you need the diagram? You can do more sophisticated calculations if you have simpler tools. So if you can simplify your calculation, you can do more things with that. So that's what Feynman did, and he helped developing the field much faster. So people can do it much faster way. He gave a prescription, he gave a calculator, for example. He gave a calculator to calculate. So that's this diagrammatics is a calculator. You draw it in terms of diagrams, you know all the answers much faster way. Okay, so both of them got Nobel Prize due to this. Now the diagrams can look like this. So again, horrible looking, but I just wanted to say that all you want to do is an integral. Okay, and to represent the integral, you need diagram, and those are called Feynman diagram. Okay, this is the famous Feynman diagram. And note that this is not related to just field theory. It is used in any perturbation theory you will do in life. Let's say multi-particle quantum mechanics. Let's say probability theory in mathematics. In all possible theories, if you have perturbation theory involved, you will have diagrammatics, and it will help you extremely. Okay, so that's very important. It's not related to the thing I am saying. It is everywhere. Wherever there is a perturbation theory, there will be diagrams due to Feynman. Okay, and it is not related to any particular theory like quantum electromagnetism. Okay, so we have not talked about QCD yet. Those are all QED, quantum electrodynamics, not quantum chromodynamics. And I don't know how I'm doing with time. Okay, so what happens in QCD? Now QCD is almost similar to QED. There is no difference. As I said that you need a strong interaction. I will explain why it is strong, but it is exactly similar to QED. Yeah, there is almost no difference except the fact that there was an electromagnetic field, like electric field and magnetic field. These were single functions. I mean, single function means it is three functions due to the coordinates. But other than that, there are one vector function. Okay. But in QCD, you have another two indexes. These are called internal symmetry indices. Okay. The point is that there are n number of fields involved. There are, let's say, I and j run from 1 to n. So roughly, there are n square number of electric field, there are n square number of magnetic field. And these are different from the electric field and magnetic field you know from the electric field. So this is a different kind of electric field and magnetic field, but the natures are more or less same. Okay. And as you had electrons, like psi is the single field. I mean, barring the fact it's a fermion. There is the one field. Now we will have quarks, which will have another one index, the same index. So there will be n number of quarks. Okay. For our nature, we have this n, capital N is 3. Okay. So we have three quarks, three types of quarks in master part. I will not go into that. The most important point is the uncanny similarity between the QED and QCD. Okay. Yet you will see how different they are. Okay. And the difference is this: that there can be 3 electrons. you knock out an electron with high energy photon, like any experiment you do, like let's say compound scattering or whatever, electron can knock out from an atom and it can be charged, right? So it can travel through space without any travel, right? But one important observation in QCD or in strong force, these are experimentally verified, that there is no free quark. A single quark cannot travel in free space without having another quark associated with it. So the force is so strong that you cannot get a single free quark in an experiment. Okay, so you can separate electron and positron or whatever, like the center. You can separate, let's say hydrogen has one proton, one electron, you can separate it. But you cannot separate one quark from another quark if they are interacting. Okay, that's the difference this particular change makes. Okay. And it forms only bound state. It cannot be found free. It always forms bound state. Bound state between quarks, antiquarks, and these are called mesons and hadrons. You must have heard of like protons, let's say. Proton has 3 quarks. These are in a bound state. Proton is like a bound state of quarks. Okay, that's the idea, that it is always a bound state. Quark cannot be free, okay, in experiments. Now you can ask, what is the force? Okay, the force in unity is used to have R squared, the same electrostatic force. Okay, roughly, if R is more or less significantly higher. The force in QCD is constant. What does it mean? If R goes to infinity, or let's say 10 kilometers, it is significantly low for electromagnetism. But force is same. If you take 2 quarks and separate them by 10 kilometers, still the force is exactly the same as it will be like if they are one Fermi. You see that the force doesn't change. It's like you cannot destroy field lines. They will stretch, like it's like it is connected through some rubber band or something. It cannot be detached at all. If you try to pull it, let's say 10 kilometers, the force will be exactly the same. So that means it's an extremely strong force than the electromagnetic. Okay. So this is the main point, and that is the main reason why protons are so stable. Like why protons or the bound states in the nucleus are so stable, because they are constantly interacting through this particular force, which is constant even if you separate them by a long distance. Okay. That's the main point, that is extremely strong force. And in pictures, in QED, electron creates an electrostatic force around that particle, because that's why it interacts. I mean, there are interactions between the charges because of that. And the force line looks like this, as you know. Okay. And as I said, these are mediated by photons. I mean, electrons interact with electrons or positrons to exchange the photons, as I tried to explain in the beginning. Now, the same particle for QCD is called glow. So, for example, E and B are the fields for the photons. These E and B are called gluons. Okay, this is just a name, but it's a different. It plays the similar role of photon. Okay, it helps quark interact with each other. This is a particle which helps interact with. Again, you will not find gluons free. Like there will be no single gluon. There can be bound state of gluons. Those are called gluons. But the main point is more or less same. But here the main point is that the force lines are extremely spreaded. Okay, for electric charge, the force lines are extremely spreaded. For what happens? The force lines are not so spreaded. They are confined in a single tube kind of an object. So the force line, there is no force line, let's say here, going from this. These force lines are extremely confined to a single tube. And that is the effect, what happens if you just put another couple of few fields, like how I did the IJ. Just put IJ indices and you will see the force lines are suddenly combined together in a single flux tube, like tube kind of a thing. Okay. These phenomena is so confined. And an important point, this is an open problem. People couldn't show why you just add few fields and why this happens. They showed it numerically that it happens. You take the theory, you do it, and you see. But analytically, there is no way to know how there is no analytical way to check that this is happening. So numerically, this is insane. And that's the numerical result from problem 3. That this is the quark and the quark, and you see the past tubes, how this is looking like. Okay, don't look at the surface. This is the main picture. Okay, the surface is showing the potential, how the potential looks like. But this is the tube. Okay, and this is exactly like this. Okay. Okay, so as we saw that two quarks interacting through gluon looks like this. You can almost approximate it like this. That two quarks attached by a string-like object, just a rubber band or whatever you can think of. It has some tension. The force is constant in the rubber band, and that's how you can think of it. Now this is caused by this person in Toho, and it was explained in a more detailed way by David Ross. Okay, both of them are available in high mechanics. Okay, so previously what you were doing is two quarks interacting with gluons. What you have to do, you just learned that if you want to solve QCD or you want to calculate that particular integral, you have to sum over all possible diagrams. So that's what we do, sum over all possible Feynman diagrams. Okay, in this way. But here, if you think of it as a string attached to it, you can write a different equation of motion. It is totally different from the QCD action or whatever you wrote. Okay, you write an action for this surface, for this line, for this string object. Like you know there is a, so let's say you are trying to write an equation of motion or action for a guitar string. Okay, now how will you see? You have a string attached between the end and the rear, and that is oscillating. Now you think that there is another direction which is the time direction. Okay, now what is happening? The time direction, what is happening is it's like a 2D seat, right? If you have the space direction and the time direction, it's like a 2D surface. This is exactly like the drum we saw in the beginning. It's like a bongo surface. I mean, bongo surface was created in the 2D, like spatial 2D, but this surface you have to think one time direction, one space direction. But then that string becomes a seat. A single particle in time direction becomes a line. That's called one line if you have heard this one. A particle goes in time, it is like a line. If a string goes in time, it becomes a seed. It's a 2D surface, right? Okay. So you can write a totally different action for that, and you claim that can there be an effective dynamics for the string. That means you write a different action for the surface, and you claim that whatever answer you are trying to calculate in this side by summing over all those Feynman diagrams, can you reproduce all these results by doing this particular calculation? So it's a totally different problem, and the answer is yes. You can get a totally different description for the same object, for the same theory. Okay, and actually recently we are working on that. That's mainly our work, and this is how it looks like. That what is QCD fields? You saw E and B with IJ indices. Okay. Now I was a quarks, had an I index. These are the quarks, and this is the particle you have to do. Okay. Now in the string side, what is happening is the position of the string is a field itself. The position, it's like a drum. The surface of the position of the drum was a field. Now the surface, whatever is created by this particular string, is the field. Okay. So what you have to do, you have to sum over that position of the particle, and you have to write a very different action. And you claim that these two matches. Okay. So this is a very dramatic change in the problem. Why? Because Feynman did a particular kind of simplification by drawing Feynman diagram. Okay, the calculations are very complicated. He wrote a particular diagrammatic way so that you can do it much faster. Yet in QCD, because it is a strong interest, okay, the partition parameter is not so small. You have to expand to a very high degree to get any accuracy in the calculation. Since the partition theory doesn't work so well, you need a totally drastically different description model. The same Feynman diagram is not helping QCD. What helped QCD? QCD had a partition parameter which was very small because of the electron charge, smallness of the electron charge. QCD coupling is not so small. That's why it is also of interest. It's from both. So you need a totally different description. And this is the description. Now here what happens that the same of infinite number of diagrams in Feynman way in QCD can be replaced by a single diagram in this string theory. Now try to understand that. In QCD, what you are doing that you want to calculate that integral, you have to calculate infinite number of diagrams. But what if you have a theory where you just calculate one diagram and you can replace infinite number of diagrams? What does it mean? That infinite number of diagrams can be calculated at once. Just calculate one thing and it will calculate everything else at infinite number of diagrams at once. So you have a much faster way to generate analytical results. So numerically, it is people are exploring, but an increasing number of points. In numerics, what is the problem? The problem is creating the grid. How to increase the grid number, get accuracy due to the grid. So that's a huge constraint in numerics. But analytically, we can do whatever we want. And that is the development we can make, that only one diagram can replace an infinite number of diagrams. That's a very important development. And these are called dualities. Okay, there are other examples of duality. This is one example. This is called QCD string duality. That there is a relation between a stringy object and QCD theory. These are totally different objects to begin with, but apparently, what I will give you a dictionary. You calculate this particular quantity in QCD and you calculate another quantity in string, and they will match. I will give you the dictionary and calculate in the string inside, you will get the answer for the QCD. So you see, you replace one theory by another theory, which is much simpler to calculate, and it becomes much easier. So that's all we are trying to do, and that's how I will finish. And okay, so QCD is strongly coupled system, as I said. That is extremely strongly coupled system, and hard to calculate anything analytic. Anything due to large number of Feynman diagrams. There are a lot of diagrams involved because this is a strong interaction. And the point is that we found a dual description of QCD, a string theory. Okay, it's a dual description. There is no QCD fields, yet it describes exactly the same thing you want to describe. Okay, and it simplifies the calculation a lot. Okay, and it's a strong alternative to lattice group, lattice gauge theory, whatever people are doing. Now, although lattice has achieved a lot, but it can give an analytic control. Like, you do numerics and then you do analytical calculations, you have more physical understanding. So that's why it is very important. And the most important point is this is an unsolved real world problem. It's a QCD. It has to be solved. It's there. It's been seen for 60, 70 years in experiment. Yet there is no analytical control over the calculation. Why? Because of the strongness of the problem. It's a strong interaction. There is no perturbation theory. Okay, and a lot to be done. Okay, and if you are not enough motivated, you can look at the page from Clay Mathematics Institute. There are $1 billion associated to this problem. It's called dynamic and master problem, and this is yet an open problem. As I said multiple times, that these are open questions that people don't know how to deal with analytically. Not analytically. Numerically, you can get data, and they are not yet giving the money, so you have to get it through analytics. So that's the point, and anyone can give, and we can ask any question.
Yes, kind of a question.
Is there any connection with this to the Feynman?
And gauge. It's just so gauge theory always, I didn't explain all those things in detail, but in gauge theory, usually you have a particular symmetry. You must have seen the pi can be moved by lambda, and then you can get rid of multiplication. Feynman also had to do this problem, and he chose a particular gauge. Again, it is simplified the problem, but that's one kind of simplification other than all these things. Feynman was intelligent and he did a lot of simplifications. One of them is using Feynman gauge for the problem. So yes, it's called Feynman gauge, but
Any other questions? Audience? This is a different thing, right?
yeah. It's a totally different thing. In one line, you saw previously, beginning, here. In doing this integral, you saw that I am drawing this diagram to write down each term in the integral. So this is giving me the potential theory for the integral, not the integration result itself. Let's say if I had a way to write down diagrams for the answer itself, not the integral. So here there is one step left that you have to do the integration and then you get the result. Okay, and I am doing the diacritics for the integral itself. But if there is a way to write down the answer itself in terms of the diagram, so if you can find out a way to relate all these numbers in a geometric way, it's extremely useful. And those are called amplitude headroms. That is another kind of diagrammatics. So we don't have to do the integrals. Usually integrals are also becoming very hard to do if you go higher in powers, and that might become very complicated. So that's a problem. And even if you know the probability limit, you might not be able to do the integral in some cases. And to replace that, if there is a way that do diagrammatics to write down these answers itself. So that's people are trying. Main person is Weizmann in America. If you want, you can explore that. But that's another kind of way to do the same problem, but not the diagrammatics for this formation before the integration integral, but after the integration, to want to do diagrammatics. That's unusual later on, but that's not. But that's also an important development in the case. This is a simple calculation I want to do in the calculation. Now you can ask, so this problem is not important. I mean, this is just a mathematics example I use to explain the problem. But the important problem is that that E I have here. So this E is equivalent to lambda, right? And E is the coupling constant between the photons and the electrons. Let's say electron is passing and the photon is scattering into that particle. The electron is going and the photon is coming deep to the electron and scattering. It's called quantum scattering. Okay, that's quantum scattering. Then how strong the interaction is. I mean, there will be deflection. If there is a heating, the electron will be deflected from its original path. So how far it is deflected? So if it is deflecting less, then you will say the coupling constant is small. If it is deflection is high, then you will say the coupling constant is strong. It's very high. So that lambda represents the coupling between various fields, various different fields. That will be yes.
Seems like there are no further questions. Let us all thank the speaker. And I might add, we also expect you to keep coming back
Yes.
time to time.
And today also I am here for a few more hours.
Please.
Okay.